Welcome to the Explainer. Today we're going to be talking about linear regression. And look, I know what you might be thinking. It's just drawing simple lines on a scatter plot, right? But actually, it's so much more than that. Together, we're going to use it to uncover the foundational blueprint for literally all of machine learning.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the hello world of ML. Break down the model and its cost function, explore exactly how the model learns, scale things up to curved lines, and finally wrap up with regularization and real-world deployment.
Starting off with Section 1, the hello world of ML. Let's look at how we start with a really simple, relatable problem.
So let's ground this in reality for a second. Imagine you're looking at a spreadsheet of real estate data. You've got a list of house sizes and their final sale prices. How do you predict the price of a brand new house based purely on its square footage? Now, sure, you could just eyeball it on a scatter plot and take a guess, but to actually automate this, we need a mathematical formula. We need to be able to plug in literally any size and instantly get a reliable price out the other end.
And honestly, that is exactly what linear regression does. It is the absolute hello world of machine learning, fundamentally designed to draw the best straight line through your data. But here's the secret. Don't let its simplicity fool you. It actually acts as a sort of Trojan horse to teach you the universal machine learning training loop.
And that universal loop always follows three specific steps. Step 1, define a model. Step 2, define a cost function. And step 3, optimize the parameters. Every single ML algorithm out there follows this exact same pattern. So if you master it right here with the simplest case, you're going to recognize it everywhere, all the way up to incredibly complex neural networks. Moving on to Section 2, the model and cost function. Let's look at how we mathematically define our model and, just as importantly, measure its mistakes.
Let's break down the anatomy of this loop, starting with the model itself. The formula is y equals w transpose times x plus b. Now, what does that actually mean? Well, w is our weight, basically the slope. It tells us exactly how much y, our predicted house price, changes when x, our house size, goes up by just 1. And b? That's the bias. It's essentially our baseline value when x is precisely 0.
Okay, but how do we actually know if the line we drew is any good? We have to measure how wrong we are. And that brings us to our cost function, mean squared error, or MSE. It's a single number that neatly captures the total error of your predictions. I want you to visually picture this cost function as a giant, smooth bowl. The very bottom of that bowl-like surface, that is where your error is minimized. So training your model literally just means finding your way to the bottom of that bowl.
So the crucial point is, why do we specifically use squared error to measure our model's performance? Well, there are two huge reasons. First, it disproportionately penalizes large errors. If your prediction is off by 10, mathematically squaring it makes it 100 times worse than being off by 1, not just 10 times worse. Second, squaring the error creates a perfectly smooth, completely differentiable surface everywhere. That makes the optimization math so much easier to handle.
Which brings us right to Section 3, how the model learns. Let's talk about actually finding the bottom of that bowl.
All right, so we've measured our errors. Now, how do we fix them? We basically have two main tools for this. On the left, we have gradient descent. It iteratively takes little steps downhill until it finds that lowest point, which makes it absolutely perfect for massive data sets. On the right, we have the normal equation. This solves the whole thing in one single mathematical step via matrix inversion. It's super elegant, but there's a catch. Because matrix inversion is an order of n cubed operation, it completely chokes if you try to feed it millions of rows. Gradient descent, on the other hand, handles that scale beautifully.
Now, what's really interesting about this slide is how perfectly everyday layman's terms map directly to the technical reality. When people say walk downhill, what they really mean is gradient descent, iteratively adjusting your parameters in the exact direction that reduces the cost function. Step size? That's your learning rate, a scalar controlling how aggressively those parameters change per step. And solve it directly refers to the normal equation, working its magic to give you a closed-form solution without a single iteration.
Let's zero in on that learning rate for a second, because getting it right requires a really delicate balance. See, the gradients tell us which direction to move, but the learning rate dictates exactly how far to step. If you set your learning rate too large, you will literally overshoot the bottom of the bowl and your model will completely diverge. But if it's too small, taking tiny microsteps, your training will take forever. Typically, you're going to want to start with something like 0.01, 0.001, or 0.0001.
Moving to Section 4, Scaling Up and Curving Lines. We're going to expand our foundational loop to handle multiple features and complex shapes.
Let's make things a bit more real-world. Houses obviously aren't priced just on size, right? Bedrooms and age matter a ton too. So multiple linear regression fits a multidimensional hyperplane instead of just a straight line, while still updating all those weights simultaneously using MSE. But beware, you absolutely must use feature scaling here. If your prices are in the millions and bedroom counts are in the single digits, your cost surface becomes extremely elongated. Standardizing those ranges by subtracting the mean and dividing by the standard deviation fixes that stretched out bowl shape so gradient descent can actually converge faster.
But what if your data isn't a straight line at all? What if it curves? Enter polynomial regression. We can actually fit complex curves by feeding the model nonlinear features, things like x squared or x cubed. And the brilliant part here? The underlying math remains strictly linear in terms of its weights. We are literally just giving our straight line math curved input features to play with. It's such a clever trick. There is a massive trap here, though. Overfitting. Let's say you use an incredibly complex model, like a degree 10 polynomial. Yeah, sure, it might perfectly pass through every single point in your small training dataset, but all it's really doing is memorizing random noise. It's completely missed the actual underlying pattern, meaning it will be practically useless when you ask it to predict accurately on new, unseen data.
So how do we actually grade our model to know if it's doing a good job? We use the R-squared score. A 1.0 is a perfect score, flawless predictions. If you get a 0.0, well, your model isn't doing any better than if it just blindly guessed the average value every single time. And honestly, yes, you can absolutely get negative scores. That literally means all your fancy complex math is performing worse than just guessing the mean.
Finally, Section 5, Regularization and Real-World Use. Let's talk about self-correction and how we actually deploy this code into production.
How do we actively prevent the model from just memorizing data like we saw with overfitting? We use ridge regression, also known as L2 regularization, and this brilliantly illustrates how the model can actually self-correct. We add a mathematical penalty directly to the cost function to aggressively shrink down large weights. You use a hyperparameter called lambda to control this exact trade-off between weight size and regularization, keeping the model perfectly generalized.
Okay, let's look at how this translates into your actual workflow as a practitioner. Bridging that gap between textbook math and real-world software engineering happens in 3 simple steps. Step 1, generate some sample data to test on. Step 2, build the linear regression loop entirely from scratch in Python so you truly understand the math in your bones. And Step 3, put that custom code away and use a dedicated library like Scikit-Learn to actually run it in production. Now you might be wondering, why go through the trouble of swapping it out? Well, building it from scratch on the left is absolutely crucial for building your deep understanding of the ML loop. But on the right, established libraries like Scikit-Learn are built for reality. They handle all the weird edge cases, ensure numerical stability, and are heavily optimized for performance so you can reliably run massive systems like demand forecasting models without a single hitch. And there you have it, the complete architecture of the machine learning loop, perfectly illustrated by its simplest application. You now know exactly how to define a model, how to measure its errors with a cost function, and how to optimize it using gradient descent. So, now that you intimately know the ML loop inside and out, what regression problem are you going to solve from scratch next?